Okay, so today we are going to be going over the 1976 AP Physics C Mechanics question number 2. So, the question says a cloth tape is wound around the outside of a uniform solid cylinder, mass m, radius r, and fastened to the ceiling, shown in the diagram above. The cylinder is held with the tape vertical and then released from rest. As the cylinder descends, it unwinds from the tape without slipping. The moment of inertia of a uniform solid cylinder about its center is 1/2 mr squared. And so part A asks us on the center, on the circle above, draw vectors showing all the forces acting on the cylinder after it is released. Label each force clearly. So when the cylinder is released, it's still attached. Part of the tape, as it says in the problem, is still attached to the ceiling. So there's going to be some tension as it falls, right? Because that tape's going to pull on the rest of the cylinder as it falls, and we'll label that T. Also, because it's in free fall, the only force that is acting on this tape as it falls is its weight, and that's going to be acting from the center because, although it's probably a hollow cylinder, all of this would essentially, mass on the outside of the rim would concentrate into the center, and weight, the force of weight is equal to mg, capital Mg, because it tells us right here that it's a mass m. All right, next, in terms of g, find the downward acceleration of the sphere of the cylinder as it unrolls from the tape. Well, first let's start by summing our forces. So let's sum our forces in the x direction. And well, like I said earlier, this thing's just in free fall, it's falling straight down. There are no horizontal forces, so our sum of forces in the x direction is equal to 0. Now let's sum our forces in the y direction. Now, if we want to find our forces in the y direction, we're going to look at our image above, our free body diagram above. And, oops, forgot the y. And also, that's going to be equal to ma, mass times acceleration. And so if we look at that image above, if we sum our forces and if we call the downward direction positive, so we have mg positive minus t is going to be equal to ma. Now, there's not much we can really do here. In terms of g, find the downward acceleration, we still need to solve for some variables. And so we're going to do that by creating a torque diagram. And so I'm going to redraw that cylinder. And now we're going to have to think about what forces would be causing torque on this cylinder. And so here's our radius of it, and let's think about our two forces we have. Which one would be causing torque, or if both were, if none were? Well, the weight is going through the center of the sphere, so it cannot be causing torque, because in order to cause torque, it has to be a distance away from the center of mass, which is concentrated at the center of this. So it can't be the weight, but the tension acts at a distance r, or the radius of the sphere, which tells us in the problem is r, away from the center of mass. And so our tension is going to cause a torque on the cylinder. Now, in order to find the direction of that, you would have to do the right-hand rule. And if we think about it, I mean, I can't really show you, but your fingers would go out this way and then curve upward, there's essentially your radius. The tension would curve upward, and you'd end up having it'd end up spinning that way, rotating that way. So our acceleration, well, that's really bad. Angular acceleration is going to be like that, if that makes sense. So if we sum our torque, that's going to be equal to I alpha, or the moment of inertia times the angular acceleration. Like we said earlier, the only torque on the cylinder is the torque caused by the tension, so I'm going to label that torque T, and that's going to be equal to, well, our moment of inertia from the problem, 1/2 mr squared, which is the moment of inertia of a hollow cylinder. And then that's going to be times our angular acceleration. Well, angular acceleration, another way of putting that is just a, our linear acceleration, over r, right? Because angular acceleration is just a over r. So, all right, what will torque T be? Torque T. Well, torque is the cross product of the distance or radius away from the axis of rotation and the force that we are looking at, and that is producing that torque. So, if we're looking at force T and the torque it produces, it is a distance r or a radius r away from the axis of rotation right here. And because it's 90 degrees, we can just say that the torque produced by that force is T times R. Now that's going to be equal to, well, let's look over here. We have R squared over R. That's going to reduce this to just 1 and cancel that out because, R squared divided by R just leaves you with R. So you're going to have 1/2 mRA. And so, again, what we can do is we can divide by R because we have an R on both sides. And that leaves us with T equals 1/2 mA. So now that we have something that we can use in the other equation that we can solve for G, we're going to take this and plug that in up there. So, mg minus, let's plug it in, 1/2 mA has to equal mA. M's a term or is part of every term on both sides. So we can divide by m and get rid of that. So cancel the m's. What we're going to be left with is G minus 1/2 A has to equal A. Well, part B wanted us to solve for A. Let me label this as part B. Part B wanted us to solve for G, And so when we solve, wanted us to solve for the acceleration, the linear acceleration. It says the downward acceleration at the center of the cylinder. That is our A, linear acceleration. It wanted us to solve for that in terms of G. So when we do that, we're just simply going to get 3 over 2. A, if I add to one side, equals G. So that means that A equals 2/3 G. And there's our answer to part B. And now part C, it says, while descending, does the center of the cylinder move toward the left, toward the right, or straight down? Explain. This question may seem complicated, but it's actually fairly simple. So the best way to think about this is, because there are no horizontal forces acting on the cylinder, like I said, whenever it falls, the only forces acting on it are the object's weight and the tension, because, as we said earlier, it's attached to the top. Well, in part B, we looked at the tension, and the tension is on the rim of the cylinder, and that tension is causing a torque on the cylinder. Now, that torque isn't going to change the upward, downward, or even horizontal movement at all. It's just going to produce a torque, a rotation in the object. However, the object's weight, it's acting at the center of the object, and it's pulling it straight downward. And so that's going to produce an acceleration downward because force equals mass times acceleration. And that weight, which if we look at the two forces that are acting on the object, the torque and the weight is what's going to move the object downward. And like I said before, there are no horizontal forces, so the center of mass of the object will simply move downward. Although parts in the rim are going to rotate, the center of mass of the object will just be moving downward. Right, it's in free fall, straight down, no horizontal forces. So because there are no horizontal forces, acting on the cylinder, the cylinder moves straight down. And that's a very simple, concise way of putting it. And so that answers our question to part C. It does not move to the left, not to the right, it just moves straight down.